Hello everyone, again Dr. Bellman here with the presentation of another video for my General Chemistry 1 courses. In this video we will keep talking about ideal gases. Very well, so let's go change into the pen mode. There we go. And write down ideal gases. That's our subject of study, there we go. And if I draw a box and I put a bunch of dots inside of them, basically I'm talking about what? An ideal gas. Awesome. And I also know that the equation that will describe an ideal gas is going to be PB, the same as nRT. So very simple, very emphatic, very effective also. Right? Some of my students have asked me, Professor, which gases I can model with the ideal gas equation. I would say basically anyone, as long as you use a small amount, but for teaching purposes, right, we will say that everything can be modeled right now because it's the subject of our study, right? To be honest, the best in which it works the best is for these two, but it doesn't matter, right? Now, we're going to say that it's going to work basically for every single one. Awesome, very well. So last class we were saying that there are different variables that we can consider in this equation, right? One is pressure, the other is volume, the other is temperature, but there is also another one that is quite interesting, which is the number of moles, right? Because chemists, like me, like to know as much as the system as they can, and the number of moles actually will tell you a lot about your system. So if we are smart enough to go and clear this equation to the number of moles, we will see that there's a direct correlation between what? The multiplication between pressure and volume over the multiplication of RT. And this is very important. This is very important. You see, I can measure in my system the pressure, I can measure in my system the volume, and I can set or measure the temperature in my system. That means that when I set these three, right, and I correlate directly to the inverse of the concept of gases, what I will be describing is the number of moles. Big deal, major deal, right? Because we are chemists and we like to count molecules. Knowing the number of molecules will tell us a lot about our system. And there are other definitions that we can use for the number of moles. And one very important one is molar mass. Okay, and molar mass is going to be described as this weird M, right? This is this. And molar mass actually, guess what, has a direct correlation also with the number of moles, but not also the number of moles, but the mass of a compound. In this case, M correlates with the mass. Very well. So let me clear a new page. Awesome. And I know that N, there you go, I know that N is the same as PV over RT. Right, and I also know that the molar mass, right, has a direct correlation between the mass of the compound over the number of moles, right? Now, molar mass can also be identified as something that we all chemists know, the name molecular weight, right? And it makes sense because with the molecular weight, actually what we use, knowing the formula, is calculating the number of moles. So I don't know if you see what I want to achieve. What do I have here? I have N, and what do I have here? I also have N. So what about if I clear both equations and try to see what is going to happen here? So this one will remain the same, and the same as PV over RT, okay? But let's go and clear this equation for N. So now here N is going to be the same as what? As the mass of the compound over the molar mass. And look at this, what do we have here? The same N. So let's go and clear this one and continue. So in these terms, right, I know that, again, my pen, excellent. N is the same as PV over RT, and I know that N is going to be the same as M over weird M, molar mass. And since they are the same, then literally what we can do is this. The mass of the compound over the molar mass is going to give me the same as PV over RT. And now, with two different definitions, we can start modeling a more complex system. Excellent. So let's see what we else can do from here. I don't know if you are trying to follow me in terms of what we can describe, because look what we have. We have mass and we have volume. And when we clear these equations, right, we can get that m over v is going to be the same as what? As p times m over RT. And what does m over v is? Oh, well, this is density. So with a very simple correlation now, actually, we can model something with another measurement that we didn't have at the beginning, which is density, right? So let's go and model, transform this into something easier to understand. I know that m over v is the same as d, and I will write also density as this symbol, right? You can also find that in some books. And I'll use it just because it's the one that I like. So I can say now, with this correlation, that the density is going to be what? The pressure times the molar mass over RT. So it's another expression of what? Of PV, the same as an RT. Why? Because the number of moles have a direct correlation, right, with m, and m has a direct correlation with what? With density. So everything is like following tracks. Okay, very well. So now that I know that, what can I do with it? Well, pretty simple. Let's go and use a practical example to see what we can do. So I have my magic box, 3D and 2D, and I'm going to put a lot of gas there. And which gas I'm going to use? I'm going to use CO2. Okay, I'm going to say, okay, I have 0.990 atmospheres, right, of pressure inside of this container. The temperature is going to be only 55 Celsius, so it's not that hot. And the question is, well, what is going to be the density above this? How can I solve it? Well, it's actually pretty simple. It's pretty simple because we have everything to solve this problem now. So in every single terms, I know that the mass over the volume is the same as P times M, weird M, over RT. And I like to know this as what? As the density. So if this is true, right, what about if I just go and first calculate what I need to calculate and that I don't have? So do I have the pressure? Yes, I have the pressure, it's here. Do I have the temperature? Yes, I have the temperature, it's here. There you go. Right, they are asking me for the density. Okay, here is the density. So what we are missing is what? The molar mass. And if you remember, the molar mass has a direct correlation with what? With the molecular weight. And the gas that we are using actually is CO2. So in order to determine the molar mass, what I'm going to use is the formula of CO2. So very well, how am I going to do that? Pretty simple. I'm going to a periodic table and I'm going to look for the atomic weights. So carbon has what? 12 grams over mole, right? And oxygen has approximately 16 grams over mole, right? But I'm going to multiply these by 2. Why? Because I have 2 oxygens, very well. So let's continue. And if I have carbon the same as 12 grams over mole, right? Oxygen the same as 16 grams over mole, and this is going to be times 2 because I have 2, remember, is CO2, right? And I add all of this, what I'm going to get is 12 grams over mole plus 32 grams over mole, right, over, well, not over, but giving me result of 44 grams over mole. So I know that M for whom? For CO2 is the same as 44 grams over mole. Very well. So now I have everything. I have everything that I need to describe my system. So if I have my container, right, with a lot of gas, excellent, very well, a lot of gas, which gas? CO2. And they're going to ask me, well, which is the density? Well, now I know that the molar mass is going to be 44 grams over mole, right? I also know that the pressure is going to be 0.990 atmospheres, pretty good. And I know also that the temperature is going to be 55 Celsius. So, and then they're asking for the density. So, and I know the density is the same as what? As the pressure times m over RT. So if this is true, right, I'm going to use another one. Now the density is the same as Pm over RT. I can start throwing numbers to my equation and see what we will get. So I have 0.990 atmospheres, right, times the m, which is 44 grams over mole, okay, over the constant gases, which is, I know that it's 0.082 liters atmospheres over mole Kelvin, right? And remember that Celsius plus 273 is the same as Kelvin. So in this case, what I'm going to use is 328 Kelvin. So let's do the dimensional analysis. What do we get? Kelvins go with kelvins, atmospheres go with atmospheres, moles go with moles, and look what we get. Grams over liter, which are the dimensions that we need for density. So we're doing things okay. So let's go ahead and do the math. Please help me. I don't want to make mistakes like the other like the other video. It's going to be 1.62 grams over liter. Okay, and this is going to be the density for whom? For CO2. So I have now a firm more understanding of what is going on with my system. Very well. And I can start doing more things with this, right? Let's go take the pen. And in these conditions, the density for CO2 is going to be the same as what? As 1.62 grams over liter. And let's say, for example, that what if, right, the volume of my box, of my container, right, is the same as what? As 3,487 milliliters. Well, I can transform this into something a little bit more useful, which are liters. 3.487 liters. Awesome. But of whom? Of CO2. That means that if I know the volume of the container, right, that contains the gas, and I use the density for this, I will have 1.62 grams over liter, which is the density, times 3.487 liters. And I'm talking about the density of CO2, and I'm talking about the volume of CO2. So guess what? Liters with liters, and I end up with what? With grams. How much? Well, it says here 5.64, but it's closer, right, to 5. Oh, give me a second. There you go. It's actually closer to 5.65 grams. Okay, so look, by knowing the density, now I know the amount, right, of mass that I have of my gas, right? And we can keep playing this game as much as we want, because I know that the molecular weight, or the big M, right, is going to be the same as what? As 44 grams over mole. So if that is true, I can transform this into what? Into 44 grams of CO2, right, that are contained in 1 mole of CO2. And since this is a relationship, right, I can perform the inverse and give another interpretation. If I say that I have 1 mole of CO2 that is contained in 44 grams of what? Of CO2, then I wouldn't be lying. Actually, it's a true. It's just that I'm doing the inverse correlation that I had at the beginning. And if this is true, then I can also start playing with the amount of grams that I have. Why? Because I know that I have 5.65 grams of CO2. So let's go and play a little bit with the dimensional analysis, right? Because if I have 1 mole of CO2 contained in 44 grams, and I multiply this by what? By 5.65 grams. The dimensional analysis is going to give me what? The number of moles. The number of moles of what? Of CO2 and CO2. Very well. So when we perform the math, what we get is 0.1283 moles. Of whom? Of CO2. So as you can see, basically it's just a game of building blocks. Literally, we can go and play these as much as we want and as much as we need. I'm going to end up this video here because I don't want to get it too long, and I will see you in a minute with another video. Thank you.